In this video, I'll cover graph-based dependency parsing. I'll primarily focus on maximum spanning trees and provide a case example to show how they work. Graph-based dependency parsing techniques work by searching through the space of all possible parses for a given input and finding the parse that maximizes some score, which is usually based on the scores of the parse's constituent relations. For example, edge-factored approaches determine scores based on the edges in the hierarchical parse tree, where the overall score is the sum of the scores of all of its edges. Graph-based dependency parsing can sometimes be preferable to transition-based methods because the accuracy of transition-based methods tends to decline with longer distance dependencies. If you have a longish sentence, there's a good chance that it'll contain one or more dependencies where the words aren't within a word or two of one another. And you can imagine how with even a great oracle, shift-reduce techniques might struggle with that. Graph-based methods score entire parse trees, avoiding issues associated with long-range dependencies specifically. A very popular method to graph-based dependency parsing makes use of the maximum spanning tree. You might have encountered maximum spanning trees previously in algorithms or graph theory courses. They're graphs that connect all nodes together without any cycles and with maximum weights. In the context of dependency parsing, when constructing a maximum spanning tree for an input sentence, the words in the sentence would be represented as vertices and the directed edges would represent all possible dependency relations between heads and dependents. Weights would represent the scores for each possible relation based on the predictions of a supervised machine learning model, meaning that the maximum spanning tree would represent the preferred dependency parse for the sentence. To see what that would look like, let's consider that we have a very short sentence, book that flight. We'll create nodes for those 3 words and then also a root node. And then we'll create directed edges representing head-dependent relations between the nodes with different weights. The maximum spanning tree, given the nodes and weighted edges, would look like this. When constructing your maximum spanning tree, there are 2 things that you should keep in mind. First, every vertex in your spanning tree, aside from the root node, should have exactly 1 incoming edge, and you can see that that's the case in the spanning tree shown in red here. That's because a given dependent can only have 1 head. Second, the absolute values of the edge scores aren't critical. Instead of trying to find the tree with the lowest overall absolute edge cost, you should focus on finding the tree with the lowest relative weights of edge scores entering vertices. To formalize things a bit further, given a fully connected graph G and a subgraph T, we know that T is a spanning tree if it has no cycles and each vertex, aside from the root, has exactly 1 edge entering it. Furthermore, we know that we have a maximum spanning tree if a greedy selection process produces a graph fitting these specifications. Greedy algorithms won't always produce maximum spanning trees. Sometimes they'll produce trees with cycles. When that happens, it's always possible to collapse cycles into nodes. So you should just do that, rerun the greedy selection process with the updated nodes, and repeat until a true spanning tree, and thus a true maximum spanning tree, is found. Here's the formal algorithm for finding a maximum spanning tree. We initialize our subgraph T and its edges F to empty lists, and we also initialize our list of relative scores to an empty list. Then we start looping through each vertex in our full graph. For a given vertex, we find the best incoming edge as the incoming edge with the highest score and add that edge to our list F. For each of these incoming edges for the vertex, we then adjust their scores by subtracting the best incoming edge score. At this point, we check to see if T is a spanning tree, and if it is, we go ahead and return it. Otherwise, we move onward and collapse one of the cycles. We then recursively call our maximum spanning tree algorithm on the updated graph. Once we've recursively found our maximum spanning tree, we expand it back out to its original nodes, deleting the edge that previously caused the cycle and using the other edge we found instead, and the recursions can continue as long as cycles are encountered. Eventually, there won't be any cycles remaining, and then we'll have our maximum spanning tree. We can walk through that entire algorithm with our sample graph here. So we'll start out with our graph containing 3 words, the root node, and a whole bunch of directed edges between nodes. There aren't any incoming edges to the root node, but there are incoming edges to book, that, and flight. And remember, we want to find the highest cost incoming edge for each of them. It looks like for book, the highest cost incoming edge is 12. For that, the highest cost incoming edge is 7. And for flight, the highest cost incoming edge is 8. So we end up with a spanning graph that looks like this. This means that for all of the incoming edges to book, now we'll need to subtract a value of 12. For all of the incoming edges to that, we'll need to subtract a value of 7. And for all the incoming edges to flight, we'll need to subtract a value of 8. So we'll end up with new edge weights that look like what you see here. The edges we selected have costs of 0, and the other edges have negative costs. Now, it appears that there is a cycle in this graph, so we need to do something about that. We remember that we can collapse the nodes that form a cycle, so we go ahead and do that. Since we collapsed the nodes, that means that all of the incoming and outgoing edges for each of the previous that and flight nodes will now be incoming and outgoing edges for the collapsed that flight node. We recursively run our maximum spanning tree algorithm and find that the highest cost incoming edge to that flight is -1. We need to remember this edge for the next step. There are no cycles in this spanning tree that we've now created, so we can exit the recursive function by expanding the collapsed node back to the original set of nodes and edges. Now that we've expanded the graph, we once again see that there are some other incoming edges to the nodes that were collapsed together. We want to keep the edge we found when the cycle was collapsed, and therefore delete the other incoming edge to whatever original node it was associated with in order to remove the cycle. We're looking for an edge with a weight of -1 that would go from either book to that or book to flight. We find it down here. So since we want to keep this edge, which is the incoming edge for flight, that means we need to delete the other incoming edge to flight that we had previously included in our tree. We go ahead and do that, and now we see that we have a maximum spanning tree. Overall, graph-based dependency parsing is a simple way to create dependency trees for inputs, and it can handle long-range dependencies more effectively than transition-based parsing. To train supervised machine learning models to predict edge weights, researchers have experimented with a variety of features, including words, lemmas, and part-of-speech tags, previous and next content words, word embeddings, and different characteristics of the dependency relations themselves.